Welcome to Calculus. Whatever confidence you have will be tested. But don't worry, Stevenson has tools to help you. On this episode, Stevenson will demonstrate
So I want to quiz you or check you on some few things here. So I'm going to give you some functions here. What are those derivatives? What are the derivatives of those functions you see there? Okay, do you have some answers? Okay, did you get 1, 2x, and cosine of x? Good for you. Let's try the next one. So what's the antiderivative now? So when I say antiderivative, I want you to think, where did this come from? So here we go. Here's 3 of them. So that's g prime, f prime, h prime. Where did they come from? What is their antiderivative? For g prime, did you get x? For f prime, did you get x squared? And for h prime, did you get sine of x? Now, those answers are only partly right, and later you'll probably figure out why. Well, we're going to discover this and talk about this idea of derivatives and integrals. And this is a really important thing because when you think about it, Newton and Leibniz were really innovative for their time. So something like the area of a circle had been around a really long time. But when you talk about calculus and how Newton and Leibniz and others were trying to grapple with those ideas, it becomes pretty problematic. So how did people figure out definite integrals, their areas? How did they figure that out if they didn't have like some nice formula like area of a circle? For example, how would Newton and Leibniz have figured out that the integral of sine of x dx from 0 to pi was 2? Well, here's what they did know. They did know, if you think about derivatives, right? The quotients of the really small, infinitely small quantities, that's the delta y, delta x we studied, previously, can be used to figure out velocity from positions, right? That's your rates of change. But then they also knew that if you add up those infinitely small little thin rectangles, the areas, we practiced that recently, you could get position. So from velocity. So in other words, if you did derivatives of position, you would get velocity. But if you did areas under velocity, you would get position. So in some way then, they knew that there had to be some connection between those two processes. And Newton and Leibniz were able to figure that out, which led them ultimately to the fundamental theorem of calculus, which we're going to look at a little bit later. So Newton and Leibniz knew that the accumulator function would equal a definite integral. Okay, so let's talk notation here. The capital F is trying to represent the accumulator function of that integral from a to x of f of t dt. Now what they concluded is that the derivative of the accumulator function would equal the integrand. In other words, what was being integrated in the definite integral. So that means the integral is an antiderivative of f. And this is a very, very powerful tool here. So if you look at what this says that the derivative of your integral is really just your integrand evaluated at your upper bound. So how is the integral the antiderivative of a function? In your book, it walks through this process, so I want to kind of offer a little insight on it and a little explanation to hopefully help you make a little more sense of it. So if capital F represents the antiderivative of little f, then that equation holds. So if we set the equation equal to a, so in other words, instead of the integration going from a to x, it goes from a to a. See how the bounds change? Then what happens is that area is going to be 0. Right? Remember, we learned that from one of our integral properties. So if the area is 0, then we can solve for c, and we get negative f of a. Now, in the formula up above, or the statement up above, it tells you that antiderivative is f of x plus c. Now, c is some constant. We don't know what it is. It represents some constant of integration. Because really, when you do the antiderivative of a function, you actually have a plus c somewhere else. Okay? So we've just solved for c though, so that c can be replaced with negative f minus a. So that means that this whole problem now changes to f of x minus f of a, or capital F of x minus capital F of a. And that is a very powerful tool. Make sure you have this last rule right here in your notes somewhere. So this formula was huge for calculus and how it progressed it. So basically, if you want to evaluate the definite integral of your function from a starting point to an unknown point, any number, you can actually compute it using antiderivatives.